In this video I'm going to look at a Leaving Cert question from 2019. It's on acids and bases, or pH calculations. It's question 7, and it starts off with the usual way. You're asked to use equations to show that when dissolved in water, HCl acts as a Bronsted-Lowry acid. So you have to think Bronsted-Lowry is the proton donor, so very similar in 2020, but HCl, when dissolved in water, so we have HCl reacting with water. We know that we're going to write an equilibrium arrow here, but we don't need to. So when that reacts, so you form H3O plus, which is the hydronium ion, and Cl minus, okay? And it's that hydronium ion that's the source of all acid. Now, NH3 acting as a Bronsted-Lowry base. So we're going to, now we're using NH3. It's again reacting with water. But this time, the water is acting as an acid and the ammonia is acting as a base. So the ammonia is going to take a hydrogen from H2O. So you're going to form NH4 plus OH minus. Okay. Remember, this is the source of all acids, the hydronium ion. And the hydroxide ion is our alkali. Okay, because that's what happens when bases dissolve in water, they form the hydroxide ion. Explain why HCl has a weak conjugate base. Now, HCl has a weak conjugate base, so if I label this 1 and this 2, for equation 1, HCl has a weak conjugate base because it is a strong acid. What that means is that doesn't form much of an equilibrium, okay? So it's actually the forward reaction that predominates here. But your Cl minus acting as a base and going backward is extremely rare, so it's a very weak base because of the fact that the forward reaction is such a predominant reaction there, because it's a strong acid, a really good proton donor. And for equation 2 then, it's saying NH3 has a strong conjugate acid. That's because NH3 is a weak base. What that means is that that's not a reaction that overly predominates, okay? In fact, this reverse reaction is the one that would predominate, if anything. Ammonia is a weak base, so while it will deprotonate water and take the proton away, it's not strongly basic enough to deprotonate all of the water. So, because it's a weak base, the converse is a strong acid, i.e. the OH minus reacting with the ammonium ion is far more likely, okay, so therefore it's a stronger acid. NH3 is a weak base, therefore. Okay, so you're asked to write the self-ionization constant expression for water. So this is B. Part 1. We're asked for Kw. So Kw is equal to H3O plus, which is our acid concentration multiplied by our OH minus ion concentration there. The reason that's the case is because if you were to do a normal equilibrium expression, H3O plus times OH minus, for this reaction, H2O squared, this is a constant because the concentration of water is constant because it has an MR. So if you know the volume of it, you know the mass of it, you can know the number of moles of it, so its concentration you can find is constant, it doesn't change. If I multiply both sides by that, there, I'd get Kc times the concentration of water squared. Essentially that's just our Kw. Now, are the data in the table consistent with the self-ionization of water being an exothermic or an endothermic process? Justify your answer. So, as temperature increases, so this is for part 2, as temp increases, Kw increases. So, if this is an equilibrium here, as the temperature increases, essentially the concentration of my products is getting larger and larger because I know that Kw Kw or Kc is getting bigger and bigger. So if the concentration of my products is getting bigger and bigger, we know that with an increase in temperature, the system wants to decrease the temperature because it wants to cool it down. So this tells me that that forward reaction is endo, because it's favoring the forward reaction, because I'm making more products there and there because Kw is getting bigger. If I'm making more products because Kw is getting bigger and bigger, I must be favoring the forward reaction, which is endothermic. Therefore, this reaction is an endothermic process because we're getting more of the ions at a higher temperature. Or the forward reaction is favored. For the next step, we're asked to plot a graph of Kw versus temperature. So I'm just going to change the view very slightly there to quickly go through this. So the temperature is the independent variable that goes on the x-axis. Our dependent variable is our Kw. So we've got our y-axis there, we're going to do our x-axis of 60, so it's an independent variable. So we're going to spread it out a little bit. Like that. We know our results, we've got 0.1. So now that we've got our scales done, we have our points, so it's 0.1. Right there, down the bottom. 0.3 for 10. 0.7, 1.4, 2.9, 5.3 and 9.3. So there are points. We're just going to draw a smooth curve through our points now, like that. So remember, for our graph, the most important thing, you want to have your labels correct, you want to have your points plotted and spaced out sufficiently. You want to have units and you want to be accurate. Okay, so it's then asking us to use your graph to predict the value of Kw at the body temperature of 37 degrees. So we need to use our graph. So we draw a vertical line up from 37 like that, and we draw a horizontal line across like that. So our value there will be 2.3 by 10 to the minus 14. The next question we're asked, that's the 37 degrees. Use this value to calculate the hydronium ion concentration of pure water at 37 degrees. So that's what Kw is. Kw is equal to H3O plus times OH minus. But we know that H3O plus equals OH minus. Kw is equal to H3O plus squared. So H3O plus is equal to the square root of Kw, which is 2.3 by 10 to the minus 14, which gives me a result of 1.51657, so 1.52 by 10 to the minus 7. So that's the value of H3O plus there. The pH of water is close to 6.77 at one of the temperatures in this table. Find by calculation this temperature. Okay, so we need to use calculator again here. You're told the pH is 6.77. So this is part 6. pH equals 6.77. Therefore H3O plus equals 10 to the minus 6.77, which is equal to 1.70 by 10 to the minus 7. You get a result of 1.69824, so we'll just round it up there. You can keep that result stored because that's what H3O plus is. So Kw equals H3O plus squared, which we've said here, So kW equals 1.70 by 10 to the minus 7 squared. And you can just square your answer in your calculator, and you get a figure of 2.88 by 10 to the minus 14. So the question says the pH is 6.77 at one of the temperatures. So we're looking for a 2.88 in the table. That temperature then is obviously close to this one, which is 40 degrees Celsius. And that's that question done. For the graph, what's important is you plot the points accurately, your scale, your units, and you label the graph.